EU program and the Ministry of Research. We will start with the first project, HL4IT, or ET, better, that is the interaction of humans with level 4 automated vehicles in an Italian environment. I asked Professor Gobbi, who's the principal investigator of this project, to share its screen and start with the presentation. I immediately allow Gobbi to become an answer. And okay.
Thank you, Giampiero. Okay, we are ready. I'll be quite fast. I'm the principal investigator of this project, interaction of humans with level 4 automated vehicles in an Italian environment. Actually, the presentation will be threefolded. I'll start with a description, the objectives and the results. Then I'll leave the floor to Della Signorini for discussing about the analysis of the responses of the drivers. And the last part will be led by Professor Fossati from Università Vita-Salute San Raffaele, referring to the psychometric analysis. First of all, the team. In this slide, you see all the people involved in this research project. There is one team from the Department of Mechanical Engineering. I'm not citing the names, but you can see all the names in the slides. Then another team from the Department of Electronics, Information and Bioengineering. And last but not least, the team from Università Vita-Salute San Raffaele, led by Professor Fossati. Actually, almost all the activities have been conducted at the DriSMi lab, so at the dynamic driving simulator at Politecnico di Milano, with the contribution of Francesco and Paolo. I want to mention, this is the short list. Actually, there were also a quite large set of master students involved in the project, which are not listed here. The focus of the project is obviously safety. Actually, the focus is on acceptance of automated vehicles with, again, another special focus on a peculiar environment, which is the Italian environment, that has some specific aspects related to roads, traffic, and so on. In my portion of the presentation, I give you a short overview on why reasoning on automated vehicles, what is an operation design domain, what is a takeover maneuver. Then I'll describe the setup that has been used both in terms of scenarios developed at the driving simulator and in terms of sensors and subjective measures that have been developed by the psychometrics. I'll get at the end with a few slides on the method that we have developed to check the acceptance of L4 vehicles and some results. So the focus was to develop a standardized, rigorous approach for assessing the acceptance of this L4 vehicle. So we have been able to define how to measure, by resorting to a driving simulator, the level of acceptance referring to a sample of drivers. Actually, I must emphasize that the approach, the procedure that we have developed is actually applicable also to different technologies in which I have to consider the human within the machine, the interaction between the human and the machine. I will give you more details later. Automated vehicles, SAE level 4 is the focus of this project. The dynamic driving situation is defined for a level 4 vehicle within an operational design domain. The operational design domain will be defined at the driving simulator by describing the scene, by describing all the environmental conditions, and obviously, this is particularly important for the Italian scenario, all the dynamics elements of traffic and the particular situation which have to be considered. If we get to a situation in which we reach the limit of the operational design domain, the vehicle can require a takeover maneuver. So getting back the control to the actual driver. Okay. Actually, this is a non-mandatory situation for an L4 vehicle. Okay. So if the driver don't want to take the control of the vehicle will get to a minimal risk condition that depends on the actual traffic condition. We started this project by considering that there was a lack of information about operational design domains in Italy for L4 vehicles. And the information is really important for developing new rules and standards to include these features in the next few years. We will use our driving simulator. We will focus on exiting operational design domains, so we'll consider a specific takeover maneuver, and we'll try to characterize the driver. We'll characterize the driver both considering objective and subjective measures. This is the lab where we are. The key enabling technology, let's say, for this type of research activities using the driving simulator. We use our DIM400 cable-driven simulator. It features a quite large bandwidth. We have the lower portion of the simulator actuated by using cables that allows a bandwidth between 0 and 3 Hertz, and exalift allowing a bandwidth up to 30 Hertz, more or less. This allows to obtain the required level of realism that is required for implying a sample of drivers who are not actually professional drivers. What about the measurements? I already emphasized some of these measures refer to responses of the vehicle, responses of the driver, behavioral responses of the driver, and to physiological signals. Okay, these are objective measures. Actually, we considered a specifically designed instrumented steering wheel, an eye tracking device, an electroencephalograph, and an electrocardiograph. Okay, these are the main quantities, objective quantities that we employ. The colleagues will provide more details about this. Referring to the subjective measures, so the perception of what happened during this simulation, we have another list of quantities that we have considered. Some of them are analyzed by using questionnaires, like the BFI, B5 inventory to trace the personality, let's say, of the driver, that's disposition toward automated driving scale, which is really relevant for this. The presence questionnaire refers to the perceived realism of the simulation, and some of them are actually not questionnaires, but specific neuropsychological tasks, like the ANT test or the sustained attention to response tasks, the SART, that is able to quantify how the driver is able to sustain a quite long, let's say, a high level of attention concentration. These subjective measures have been measured before and after the simulation at the driving simulator. Okay, so some specific quantities have been analyzed before, other after the simulation itself. I don't have time to provide too many details. Referring to the scenarios, we had to consider the peculiarities and the complexity, I can say, of the Italian environment. So we had to resort to different situations, okay? At the very end, we consider an urban, an highway, and a suburban environment that were able to represent quite a large set of possible critical situations. In all the scenarios, we started with a few minutes of automated driving, that at a certain point with a specific triggering, there is a takeover request. Remember, the takeover request is not mandatory by considering this class of vehicle, and the subsequent engagement of the driver that I get to manual driving at the end of the simulation. A few words about the scenarios. The open one is characterized by the presence of a roundabout with a specific, let's say, critical situation. There are roadworks on the roundabout itself. So we had to introduce a temporary traffic light, and probably even more important, also the traffic flow that usually is counterclockwise in the roundabout, in this case was clockwise. For this reason, the vehicle, due to the critical safety situation, requires a takeover. It allows 10 seconds to the driver to get the control of the vehicle. Again, if the driver doesn't want to drive manually the vehicle, we'll get to this minimal risk stopping, or in this case, it's stopping of the vehicle. Another scenario, which again is quite typical of the Italian environment, is an highway with bridges and tunnels. The triggering is a strong wind gust. Last one, suburban scenario. This is an Italian city which has been digitalized, and the triggering event is a sudden fog that impairs some of the sensors of the vehicle. 51 drivers or passengers, we can call with both the names, students from Polimi and Università San Raffaele, so it's quite an homogeneous sample in terms of age and driving experience, but with a totally different degree. The probably most important result of this activity has been define a protocol to assess this driver acceptance. This is the full flow chart of the protocol, from defining the subjective and objective measures, selection of the participant, designing the scenario, how to proceed with the test itself, and at the very end, the assessment of the driver assessment. The colleagues will show you more results. I'll just show you some examples. This refers to one measure which is related to the vehicle, actually, which is the grip force at the steering wheel, actually the grip standard deviation. You see that for all the scenario, urban, highway, and suburban, we have an increase in this standard deviation that shows that the situation of post-takeover and normal driving is more demanding, or another more behavioral, let's say, measure, which is related to ice off-road time, shows that the minimum value refers to the post-takeover situation. Probably it's quite obvious because during the post-takeover maneuver, I have a higher workload of the driver that has to manage the vehicle itself. I close with this correlation analysis between objective and subjective measurements. You see that the disposition toward automated driving scale has a positive correlation with some objective measures. This is again the ice off-road time index, and you see that we have a positive correlation with a p-value, at least for the first 4 lines, lower than 0.05. So with a good significance level. That shows that during at least the driver which perceive automated driving as a good solution show a higher value of this time in which they are looking out of the road. Okay, that means that they are trusting this technology. Actually, we analyze also that before and after the test at the driving simulator, and it's even probably more interesting that this metric shows an increase after the simulation. So their level of trustness was even improved after the test itself. I close, I've been a little bit long. So we introduce a scientific methodology to define the acceptance of automated vehicle of level 4. We defined all the psychological tests and the physiological signals to be analyzed on the human subject at the driving simulator. All the signal processing pipelines have been constructed and described. I will show you many details. We have selected realistic scenarios at the driving simulator related to the Italian environment. We tested more than 50 subjects, and at the very end, we have been able to obtain insights in how drivers interact with automated vehicles that will be useful for defining rules and standards by the regulating bodies.
Metterò tutto a scrivere. Faccio Command Shift no,
Okay, good morning. C'è tutto. Okay, good morning all. It's a pleasure to be here and to present this part of the project, and that is, as Max already introduced, is the cooperation among different components in engineering, in mechanical engineering, biomedical engineering, and psychologists, and we did the psychologists to face a complex problem. That is the interesting point in this. It is the interesting point of this work, such as answering some questions, some technical questions about the measurement of the reactions of subjects, human subjects, during autonomous drive, exposed to scenarios of autonomous drive. And to do this, we, as bioengineers, we have been involved in order to measure some physiological reactions by measuring some biomedical signals. And it's a pleasure to have here in presence two people that worked intensively on this subject. Luca Subitoni, who started with this work with an assegno di ricerca assigned by the project, and after he decided to change his professional life, the work has been done and is still done by Pierluigi Reali, which is still here. So it's a pleasure to be here all together. And our work started answering to some questions. Is the exposition to a autonomous drive scenario impacting to the subjects, and is it possible to measure this impact? The final goal was to optimize, to make this condition as not smooth as possible, but as less impacting, and to measure if any kind of discomfort can arrive, and to try to find a solution to not to remove completely, but to face it. So we worked in the scenarios that already Max introduced, urban, highway, and suburban scenarios. And we started with a measurement of a signal that is particularly sensitive to changes in human subjects, in many other conditions, which is the ECG signal. And the reason why I change, okay? The reason why we decided to start with this signal is its simplicity. Is the signal to acquire it not in all conditions, but basically is one of the simple signals that it can be measured. But we decided to go to a complex monitoring setting. And in this complex monitoring setting, even the EEG signal, electroencephalographic signal, was collected and analyzed, as well as the eye tracking, the measurement of the activity of the eyes during the autonomous drive activity, and values, the force, the grip forces on the during driving. So this is a brief overview of why and which are the main results, partially summarized by the introduction by Max, that I thank you. I thank for this. The more than idea is to work on this kind of signal. The ECG signal, this signal is generated by the contraction of the heart, and it can be measured by sensors applied, electrodes, sensors applied on the thorax, on the surface of the thorax surface of the subject, but it can be taken because it is a signal perceivable even in the periphery. It can be measured and collected even by non-standard sensors. And in this case, we have a collection of different derivation of the ECG signal, from which we extracted the heart rate activity. The information here is the heart beats in a regular way. The beats are not equal each other continuously. It's not the beats does not repeat themselves. Did not repeat themselves in an exact way. They change physiologically, and this physiological behavior is regulated by the nervous system, autonomic nervous system, that is associated to emotional stress states. And so this measurement provides indirect, not quantitative, but quantitative informations, about the functioning of the autonomic nervous system, and it allows to obtain information about the involvement, the emotional involvement of the subjects. And this is the reason why a pipeline recognizing the peak is the activity, the ECG activity that can be measured, taking the higher value, which corresponds, this peaks, the QRS peak corresponds to the ventricular contraction, the generation of the beat. Don't go confused with all details. We concentrate on this activity. These beats, these peaks have a distance in time that changes, physiologically changes. We do this measurement through a pipeline like this one in order to obtain what? A sequence of values that are associated to the beat-to-beat variability. This beat-to-beat variability, heart rate variability, is the signal that we have considered in the analysis. And this signal is controlled. You see, signal isn't regular. It oscillates. It oscillates inside a certain set of values, and these oscillations, analyzed in the frequency domain or in other domain, can provide indication about what is going on with the autonomic nervous system of the subject that we are considering. So we concentrate on this signal, and we try to extract the contribution that can be associated to the autonomic nervous system, sympathetic branch that is responsible of the acceleration of the beats of the increase of the activity of the heart, and the parasympathetic, which is responsible of the decrease of the relaxation, which is more involved with relaxation. Taking and as a reference, you can also associate parasympathetic during night or during sleep, and sympathetic during day, during the activity. So the two branches work to assure an equilibrium and in the generation of the heartbeat, in the control of the heartbeat. So in the frequency domain, if we analyze, and we did it, we analyze it in the frequency domain, we can recognize some contribution. The variance, the entire variance of the signal is decomposed in spectral components, and these spectral components are associated with respiration, and with respiration is associated with the parasympathetic system, and the lower part of the spectrum, the lower part component associated to sympathetic system. So the activity that accelerated the beat. And this balance characterizes this control. So even in our subjects, these measurements have been done, and extracting some information about the prevalence of one of the other branches of the autonomic nervous system that controls the heart. Parameters we have considered, it's a complex monitoring. Okay, it's a complex monitoring, and we consider parameter. This is a key point, not only in the frequency domain, as I will describe right now, but in time domain. So parameters that are directly measured in time, but even associating to the parameter nonlinear analysis. So why nonlinear? Because the contribution given by the signals is not made only by linear components, linear contribution that can be explained by linear methods, but even by nonlinear components. So only the combination of different, not only one parameter exists explaining everything. We need a set of parameters, and this is the approach that we have used to analyze this signal. So what happens when the takeover maneuver arrives, is proposed? This, okay, in the roundabout scenario, the signal is aligned on the takeover alarm, pre-takeover, 180 seconds before, post-takeover. So you see, this is the heart rate of the subject. The heart rate is, this is the average we have here, and there is a change given, produced by the takeover, showing that the autonomic nervous system reacts to this condition. Why? Because the subject perceives a certain amount of the stress passing, taking the control of the car when the car asks to do it. So these are results. These are results obtained on the different parameters we calculate: takeover, post, pre-post, and normal driving. And the message is summarized here. It's a bit difficult to catch the point in this short time. The point is decreasing. So the main duration of the beat, such as increasing the number of beats, such as the heart rate, during the takeover, can be generated by the unexpectedness of the takeover request. So the subject is surprised by this request, and so it reacts through this in this way. And the changes are affect all parameters, not only heart rate, not only frequency domain, but also entropy, such as nonlinear parameters. So all parameters, all features contributed to enhance these changes. Moving to EEG, the things become more complex, and the pipeline implemented needs to introduce filtering, some steps. Here we have Luca and Pierre, which are expert on this. The point is remove noise. Otherwise, it's quite impossible to extract information that are inside that signal, but they need to be enhanced by these steps. For instance, this is an artifact that needs to be removed in order to analyze correctly the signal. And I go fast, and even disturbances generated by high activity can affect the signal and need to be removed too. What we calculate, what we extract are components, linear harmonic components that are inside the EEG signal. Impossible to recognize them without filtering and without processing, but that components can be quantified, can be used to quantify the effect of this signal during the different stages of the autonomous driving. In summary, this is similar to what I show for the ECG, and decreasing the rare components called big letter. I don't know how many of you are familiar, can be familiar with this, but there are components, alpha, beta, delta, and theta, that characterize the behavior of the EEG. The decrease of the alpha components during the takeover is a sign. For instance, one of the results that have been obtained is that the participants were more relaxed during the other two phases than during the takeover. So it means that the subject if the subject is not surprised by what arrives, he is more relaxed. And this it opens to conclusion that we have to prepare our subject, maybe through some not courses, but activities that can prepare our subjects to the experience they will have once exposed to autonomous driving. So this is what we have done, we have produced, and we have generated by analyzing these signals. And I leave the floor to the next presenter, which is Professor Fossati. Thank you so much.
Thank you very much. And thank you very much to Professor Gobbi for inviting me to this conclusive presentation of our common work. From my point of view, it's been a very important common enterprise shared by psychologists and engineers, in other terms, by researchers with very different backgrounds who try to understand a common point, namely, although we are able to construct highly sophisticated self-driving, let's say automated driving vehicles, how can we improve, in a sense, the acceptance of these vehicles by the human beings who are expected to be the buyers of them? Now I need to share the presentation, but I suspect that, let's see. Okay, I received the credits to just one moment, because I'm asked to use my password, which is simply my fingerprint.
I think that you need to go out and then.
Okay.
Okay.
Sì, sono tutti a uscire del abbiamo svelato questo segreto informatica.
I should be able to load and share the presentation now.
Prof, ci sente? Se volete possiamo condividere noi la presentazione.
Va benissimo, simply because I need only my second slide. Well, now I'm...
Condividiamo lo schermo e mettiamo la seconda slide.
Okay. Next slide, please. This is too difficult and complicated for me. Okay, that's it. That's the slide. Well, when Leda Antonella Somma and I, well, Dr. Leda Mastinu and Dr. Antonella Somma should be credited for being the actual developer of this measure, the DIDS, the ADS. Well, when we tried to figure out how to develop a measure for testing subjects' acceptance of automated driving, particularly during the driving simulation, well, we faced a huge heterogeneity in the empirical literature, ranging from people who were trying to derive the driver disposition towards automatic vehicles from baseline characteristics, let's say, from background characteristic of the driver, gender, age, school level, wealth, style of driving, say angry driving, fast driving, and all that stuff. Ethical perspectives on driving. I always respect the code, the driving code, and so on. Measures which were intended to capture specific aspects of perception of automatic vehicles, say a focus on safety, a focus of usefulness, a focus on the possibility of making very relaxed trips and so on. And finally, a set of measures which were not properly assessing disposition towards drivers' disposition towards automated vehicles, but rather the intentions towards carrying out specific behaviors, towards acting specific behaviors, like intention to buy, intention to use, willingness to pay for an automated vehicle rather than for a conventional vehicle, and so on. So we faced a hodgepodge of measures based on a hodgepodge of approaches. The bad news was that basically these hodgepodge of measures ended in unreplicated findings. It was very difficult to find a consistency of the scores across different studies, suggesting some trend in the data or some consistent results. Mostly, none of the measures had a clear rationale for its development, and these produced, at the very least, three major drawbacks. The first was usually poor reliability of the scores, an excess of measurement error with respect to the adequate assessment of what's purportedly should be measured by the score. Second, very poorly defined methods for assessing the measure ability to fit an homological network. In other terms, it was unclear what the measure should predict. And third, severe problems with measure structure. It was unclear if the components of the measure actually measure the same things or different things or no things at all. Based on this preliminary consideration, we tried to gather all the available measures. We obtained a first set of 32 potential indicators, and after preliminary psychometric analysis, we reduced this set of 32 preliminary indicators to a final set of 11 items, which measured basically 5 major dimensions of disposition towards automated vehicles: perception safety, need for control during the driving experience, ease of use of the automatic vehicle, driving pleasure, and how the driver felt while sharing roads with automatic vehicles and traditional vehicles, which was also part of our simulation scenarios. This measure, okay, next slide, please. No, the slide before. One slide before, please. Just not before, and one slide before. Okay. This measure was assessed as a psychometric measure, was assessed in the first sample of 590 adults with driving experience. Just to provide preliminary evidence of the score distribution that's developing Italian norms, providing evidence for its factor structure. We thought the scale is a unidimensional measure. I mean, all the items were supposed to measure one and only one thing, in particular, disposition towards automated vehicles, and score reliability. In a sense, the degree of expected reproducibility of the score over, say, hypothetically, an infinite number of testing of the same subjects. Is to factor structure, the scale was provided with strong evidence for a second-order unidimensional structure. In particular, the best fitting model was a Bfactor model with 2 method factors, say rubbish factors with no theoretical content, which were modeled according to the presence of reverse scored and non-reverse scored items in the scale. We enter reverse scored items just to prevent the possibility of yay nay random responding. the general factor and more than adequate reliability. The omega hierarchical value was 0.85. By conventional standard, a reliability coefficient value equal to or greater than 0.70 identifies an inadequately reliable score. Finally, and mostly, in the original sample, the DADS, the ADS total score, showed weak, albeit significant and theoretically relevant correlation with driver background characteristics like interest in car driving, aggressive violation scores. No, stay on the same, please. Okay, that's perfect. And also with a measure of emotional instability of the driver. Based on these initial findings, which were definitely supportive of the potential usefulness of the ADS total score, we relied on the same measure also in experimental phase of the study. And the DADS total score, as we expected, was correlated with both degree of involvement experienced by our participants during the experimental session on the driving simulator, as well as with the subjective experience of realism experienced by our participants during the driving simulation session. Finally, and that's the last slide, pre-test, post-test analysis. Perfect. Thank you, Lorenzo. Thank you very much. Pre-test, post-test analysis showed that the experimental manipulation, say the simulation experience, definitively increased significantly, as well as non-negligibly, the subject acceptance of automated driving in line with our hypotheses and predictions. Having said this, I thank you again for the attention and thank you very much.
Thank you. Okay, so we thank you, the presenters, for closing this session. Actually, we are running out of time. I don't know if there are questions, but maybe we discuss about the topic later during the break. So I give the floor back to Giampiero for starting the second part of the sessions of the morning.
Okay. Perfect. We are perfectly on time. Thank you for being here for this for the presentation of the second event that that refers to the STAVE project. So let me share the screen. Here we are. Okay. Ok.
Però lui non lo so.
No, prenderlo di qua. Ok.
Non si è tolto.
Vabbè, c'è niente. Okay, so welcome everybody. This is the final presentation of our project STAVE that actually is refers to the stability of vehicles, and the project has been carried out by Politecnico di Milano and the University of Pisa. Actually, the Politecnico di Milano contributed with two departments, the Department of Mechanical Engineering and the Department of Electronics, Information and Bioengineering. This is a project that has been funded by the NextGenEU program and the Ministry of Research of the Italian Republic. So we will present the objectives and results, then the stability of vehicle and driver, and finally the implication, very important implication that our studies has for motorsport and stability as the very first applications. The main motivation is that we would like to stave, that is to ban fatalities. The European Commission has said that by 2050, no more fatalities should occur in Europe. Unfortunately, we are far from this figure. Unfortunately, there are 1.2 million fatal accidents per year in the globe. 1 million people, it is more than a war. And there are 1.3 billion road vehicles running. Okay, despite these huge figures, we are still not understanding how the driver loses control of the car, how the driver manages to control the car in case of a edge maneuver or just before an accident is occurring. Which are the gaps? The gaps refer to the current education in stability and handling. Actually, we instruct our engineers that the stability refers to small disturbances, but usually we have big disturbances, especially before an accident is occurring. So this is a gap to be covered. And the other gap that has to be covered is that usually we teach our engineers to study the stability of vehicle only, but the stability is the stability of vehicle plus driver. So the question is how drivers loses control of the car. We have actually issued a publication on this that has been cited many times in the US, and actually this is one of the results that we will present today. So coming to the objectives of our project, we have three objectives. The first objective is actually to define digital twins of the vehicle in order to use them in a driving simulator and understand how human drivers loses control of the car. Use dedicated and proper mathematical description of what's going on, and actually use bifurcation theory, that is the proper theory that should be used in order to understand how drivers lose control. And so applying this theory to our case, and finally resort to regulating bodies with the with the objective 3, that is actually influencing how stability is studied and how engineers have to focus on the actual and important problems related to stability. So getting into more details on our objectives, actually we have to develop and validate a mathematical vehicle model to find a proper driver model to understand simulations. Then for the objective 2, to develop and validate a methodology based on bifurcation theory for finding threshold about which these terms make road vehicle motion unstable. And finally, set paradigms to for a new international standards. For example, we will have issued a report that criticizes a lot ISO 8855 because, in our opinion, the concept on stability there are not well addressed, to say the least. Okay, so referring to the objective 1, we went on track, of course, and we did for validating our models. We have developed a couple of models, one from Milan based on BI grade, and one from Pisa that is a full open model developed in MATLAB, and these models are available on our website. And then we used those models at the driving simulator to better understand how the drivers interact with the car. And we did, of course, several maneuvers, like, for example, you see the lane change. So the deliverables have been produced and are available, are open, are available on our website. Referring to the objective 2, we have focused the attention of the scientific community on the fact that normally the behavior of the driver plus the car is oscillatory. Actually, the drivers in edge cases are actually driving the car, and overall the motion is oscillatory. This is, I would say, easy to be seen and understood from this movie. The actual fact behind is that there are limit cycles that will have to be understood as being core concepts for actually designing new vehicles. Limit cycles actually are very much related to safety, but also efficiency and let me get it. Sorry. And comfort. Our colleague will get into details on this topic. Let me go ahead. Referring to the third objective, which is regulation, we have issued a report, as I said, which criticizes ISO 8855, and another one is being issued referring to regulation 157 that refers to the automated driving of level 3 cars. Of course, in the project, we have also focused on communication, exploitation, outreach. We had a number of YouTube and webinars devoted for the public bodies. We wrote 20 papers, 8 on international journals, and more are being submitted and will come in the after the project has been finished. And we have organized an international congress, AVEC 24, that was held from 2 to 6 September 2024. We had 103 presentations, 250 delegates, and 55 universities or research centers from all over the world. There were University of Cambridge, Berkeley, Tsinghua, Tokyo, TU Delft, Chalmers, Aachen, and so on. Here is a picture of the Congress. We had also other outreach activities. We are particularly proud to have involved also high school students that had a first and basic explanation of how drivers may lose control for their early understanding of safety issues related to vehicle. The deliverables are at our website within the DrivingSimulator website. And now I leave the floor to my colleague Fabio Della Rossa, who will get into more details referring to stability of vehicle and driver.
Yes, effectively, I go deep in what Giampiero presented as objective 2. Problem of vehicle stability. Giampiero already told that is a problem that has been studied in a huge way. I just, by chance, I was preparing the slide, I thought, let's see how many papers contain the word vehicle stability. And there are more than 50,000 papers that in the title has vehicle stability. So it's a very well studied problem, and it has been also normed, as Giampiero said, and he was also saying that they are not all useful, all those papers, he said. And why they are not all very useful? Because, as Giampiero said, normally when we study vehicle stability, we use an approach that is based on linearization and simple system. And this is what we teach also in our university. Take a very simple model, look at its linear version, or take the direct linear model, and what you obtain at the end is the great truth that every mechanical engineer knows, and that is written even in the norms, in legal norms. That is, if you have a vehicle that is oversteering, it's bad. If you have a vehicle that's understeering, everything is fine. You are sure that everything will go fine. And this truth has two main problems, has two limits that Giampiero already told us. The first one is that since it's based on linearization, it is true locally. So just for very small disturbance, I'm a mathematician. I could say that I'm a mathematician, and I'm a mathematical engineer. And so the disturbance is infinitesimal. And so normally disturbances are not infinitesimal. They can be very big, but wind gust or a maneuver that we have to do in order to avoid an obstacle. And so these disturbances are not covered by linearization. And second, in my opinion, the most important part is that the fact that the vehicle is stable does not mean that a vehicle follows a certain path. Normally, I want to go in that direction, and if after a disturbance I start going in this direction, okay, stability and path following are two different concepts that cannot be treated separately. And this is where the STAVE project starts. The idea is, okay, take the very simple model. We do not need a harsh model. in order to find our result. But don't use it alone. First of all, remember that the vehicle has a path before that you have to follow. And so couple it, study a simple model in which there is at least the scope of this vehicle. That is following a path, even a very simple path, even a straight path. So study these two models together, coupled together. If we study the two models together, the hard model that we have to study, and it is hard because we pass from two equations, very, very simple model, to 4 and let's say 6, 7 equations, is the following. This is the model, the simple model that we have studied in order to try to understand how drivers and cars work together in order to follow a path. And this model was not sufficient in order to make a convincing arguments, you know, that we were not saying just pure mathematics. But the idea of the STAVE project is find things in this model that is the simplest model you can use that has inside both how the vehicle works and how the drive works, together with an experimental validation that has been done in just after this door, I guess, if I'm correct. So let's start with the very first result that we were proud that is in that article, which the title is "How Driver Lose Control of a Car." That is done just looking at the linear analysis of this model, in which there is both the driver and the vehicle together. So we are not coping with the problem of big disturbances. Let's talk about infinitesimal disturbance. And if we look at this linearized model that couple both driver and vehicle, what we obtain, this is just how is the state 0 is the state that we want, that if it is stable, it means that we are able to following a straight path. But what we obtain is that analytically for this model, we can prove that there is always a speed for which the vehicle plus driver system is not stable anymore. This equilibrium of the vehicle plus driver system is not stable anymore. This means that independently, if the vehicle that one person is driving is understeering or oversteering, if you go sufficiently fast, you cannot drive it. But this is not a thing that it's if you go in a pub and you drink a beer, you can say that, okay, if I'm going 600 kilometers per hour, I don't think that I'm able to follow a straight path. It's nothing strange. We have proven it analytically and mathematically, and we have proven, and here is where enter bifurcation theory. We have proven that when stability is lost, there is an half bifurcation. That means that there is a limit cycle that is involved in this bifurcation. Here I have the picture of the two possible scenarios that happen. Here you see there is this green line, is this equilibrium for different forward velocity that at a certain point becomes red. And that means that there is a stable equilibrium here at 80 kilometers per hour. I can follow this, I can follow my path. Here at 140 kilometers per hour, I cannot follow it anymore because it is unstable. And what happened when stability is lost? It happened that there is a limit cycle that can be either stable or unstable that shrink. That starts with a very, very small amplitude and that generate, if it is stable, small oscillations as a possible behavior. or if it is unstable, that just cause the loss of stability of this. These are the two possible scenarios. Though this limit cycle, you see, those are the two possible features that one have. So this is where this is called subcritical out bifurcation, where there is this unstable limit cycle, and there is the supercritical out bifurcation when there is the stable limit cycle. What we have seen is that even when we are in the case in which there is the supercritical bifurcation, so that your start, you are going forward and increase speed, you start making small oscillation, and then the oscillation increase. If you, after a certain point, this way of working of the system, this asymptotic behavior of the system that is having very big oscillations, become unstable too. And so in both of these cases, there is an unstable limit cycle. And this was the limit cycle that was talking about Jean-Pierre before. That is a limit cycle that is of saddle type. What does it mean, saddle type? That has some directions that go toward the limit cycle and some direction in which you are repelling from the limit cycle. The saddle effect is this one. So you think this equilibrium is a saddle. So there are trajectories that you can start pushing with a certain initial position of your ball and a certain velocity. You can exactly stop on the top of this hill, and this is the stable direction of this saddle. Otherwise, if you are not in this case, and this is not the case, for example, you can reach almost the saddle, the equilibrium, but at a certain point it starts the other direction in which you diverge from the saddle, and then so your ball go away. Why saddles are important in system theory? Because saddles in general, with their stable manifold, divide the basin of attractions of different stable equilibrium, stable way of working. So if, for example, in this figure, I have two ways in which my system can work, ball stay on the left part, the ball stays in the right part, the saddle and the trajectory, all the trajectories that stops exactly the saddle are divided the initial conditions for which my system, my ball will stop here from the initial conditions from which my ball stops in the other on the other side. This is why saddles are important, and our saddle limit cycle has exactly the same makes exactly the same work. So this is the limit cycle. The limit cycle has a trajectory that going spiraling. This green cone goes to the limit cycle, and this is its stable manifold. While this other has another trajectory that spirals out from the limit cycle. That means that it goes to the limit cycle if I go backward in time. This is the idea of the unstable method. Those are the two unique trajectories. So all the trajectories that start in one of the points of these cones are the trajectories that go to the limit cycle forward or backward in time. All the others, just as for the ball before, approach the limit cycle and then go away. And what I was saying before, that the stable manifold of a saddle is what that divides the basin of attraction. And then also here we have a stable manifold of a saddle limit cycle, that is this green surface, and all the points that are in the green surface at the end will reach this equilibrium. All the points that are outside this green surface approach the limit cycle and then it goes away. This is how the systems work theoretically. That means that I have the equilibrium. The equilibrium, you remember, is green, is the fact that I can follow my path. system plus driver system can follow the straight path. If I have an initial condition that is inside the stable manifold of the limit cycle, is after a transient, my system, vehicle plus driver, will come back to the equilibrium. So eventually, it will be able to follow the straight path. If instead I'm outside from the stable manifold of the limit cycle, the natural behavior of my system will first goes close to the limit cycle because it's a set limit cycle, and then goes away, goes in another equilibrium that can, or just simply in a wall. This is the easiest way, where the easiest place where you. Understanding this allowed us to define to answer the other question that I said before, that is, which is the extent, how big is a disturbance in order that my system, vehicle plus driver, can absorb? How big can be a disturbance in order that I will not just exit, have an accident? And how we answer it? First of all, we remember that in our model, the disturbances that are forces or moments on our vehicle can enter only in the first two state variables, the lateral speed and the yaw rate of the vehicle. And so, since a disturbance instantaneously can modify only these two variables, since the disturbance can input only in these two state variables. And since the stable manifold limit cycle, the limits to the best of attraction, we can understand that would the limits, would say how big can be a disturbance in terms of force or moment, is the intersection between the stable manifold of the limit cycle and the VR plane that we call the ismaver. Okay, this is all the mathematics. The mathematics says there is the limit cycle, you look at the intersection of the limit cycle with the real plane, and you find how big can be a disturbance in order to be absorbed by the system, so I can I avoid the accident or not. And obviously this was not sufficient. This was the video before. We have to say, okay, this is mathematics. Is it true? And this is the stable approach. And we have tried to make an experimental validation. The first question was, it is possible to find, does this central limit cycle exist? Does exist this trajectory that you approach and then you avoid? And here, this is the video that Giampiero showed you before, in which you see effectively these oscillations that vehicle plus driver does. And we have also find in the simulator trajectories that makes many loops around a closed trajectory that seems a closed trajectory that seems on the inside. And these we say experimental validate the existence of a limit cycle. And this was interesting, the fact that if you want to do these experiments, we can do only with a simulator, because obviously you cannot ask, we have tried. Once we went, where we went in Rome, something, and we asked it to a pilot, okay, we have to find a limit cycle, so you should try to steer and stay on a trajectory in your oscillate. Said no, simply no, we cannot do that. While in the simulator we have done it more or less. And the second fact that we have said, there is a limit cycle, and the intersection of stable manifold of the limit cycle with the VR plane delimits the best of attraction. We have tested by giving to the simulator some initial conditions that were in the neighborhood of the intersection of stable manifold of the limit cycle with the VR plane. and this boundary was computed using the simple model, the 7 order model, just with obviously with the parameters that were tuned both for the vehicle and for the driver. And what we have found is that effectively, if the disturbance were much smaller than this boundary, or the drivers were able to, the simulation goes at the end, the driver were able to absorb, to go straight after starting from this initial condition. If they were bigger, it could not. Those are the meaning of red and green dots here. And exactly when we expected with our simple model, with our simple analysis, that the situation was a bit fuzzy. In some cases it goes in one direction, in the other case it goes in the other one. We have found, even experimentally, this fact. I have another couple of minutes, I would say. Okay, see if we also went further, but this is just theory, and we have not also experimentally validated it yet. This is a future work that we want to do, and it was to how we can use this information in order to detect an unstable motion, to detect an instability. And the idea is, okay, if you know that there is this boundary, you can try to measure how far you are from this boundary in order to detect if a motion is stable or not. Here you see, obviously, the green trajectory starts very inside the boundary, and it goes fastly to the equilibrium, while the yellow and the red trajectories that starts very close, one goes to the equilibrium and the other one goes away, the red one. And this trajectory for the very for the first 2 seconds of the time are exactly the same. But one is a trajectory that we can that does not cause an accident, and the other one, yes. Can we distinguish them? We have tried to use this idea of understand if we are inside or outside the stable manifold of the limit cycle. And what we have done, this is done using blockade theory. We have tried, the idea is, okay, you take a point and you project using this point in a new coordinate system in which you can easily measure if you are in one side or in the other side of this surface. And at least numerically, this is done only numerically, we have not done it experimentally yet, at least numerically, what we have seen is that we are able, using this change of coordinate, to detect if a trajectory will go toward the equilibrium or will go away from the equilibrium in even when the two trajectories are very similar one to the other. And we also made a comparison. Normally, if you want to use it in order to activate, for example, an ESP that allow you to avoid the accident, normally one rule of activation of ESP is that you have that beta should be less than 6. This is one golden rule that is used. And for this trajectory, beta is bigger than 6 at after 7 seconds. With our method, in theory, we are able to distinguish these two trajectories after alpha second, that is 10 times before. And this is that's it.
Thank you very much, Fabio. Now I invite the colleagues from the University of Pisa. Let me see, just a moment. Okay, I allow at first Professor Gabbicini and then Engineer Gulisano to share their screen. Let me okay. Marco, now you are now you can share your screen, and then we will allow Engineer Gulisano to go on. Thank you.
Okay. Just a moment. Okay, switch. Okay, good morning, everyone. Can you see the presentation?
Yes.
Okay. Okay, great. Thank you very much. So thank you for this opportunity. My name is Marco Gabbicini, and with Professor Guigiani, we have basically coordinated the team from the University of Pisa regarding the activities within the STAVE project. I would like to quickly also present our team. So basically, the team is made by PhD students. So Martino Gulisano is going to deliver a presentation after me. Matteo Mazzoni, Vincenzo Palermo, and of course Professor Guigiani Massimo is connected and on with the camera. I would like to basically to give a very quick glimpse about the main research directions of our team. The first topic that we studied was basically to introduce stability and robustness guarantees in motorsport planning and tracking, and I will give you, I mean, say 2 words afterwards. And also we have developed some optimization-based methodologies to estimate safe region of attractions of the vehicle with driver system. So basically along the same line presented by Fabio Della Rossa just before. But I will leave the second topic to Martino, and I will just give you a couple of hints about what we have done regarding stability and robustness in motorsport planning and tracking. So basically here in this work, what we have studied how robust and disturbance-aware reference trajectories can affect real driving performances when they are followed by professional drivers. So what do we mean with that? So trajectories come from the a planning framework where basically uncertainty is explicitly propagated and used to tighten the constraints, while we keep lap times as the main objective. And we compare basically 3 reference trajectories, a nominal one, a trajectory robust with respect to track limits, and one robust with respect to friction limits. We also performed experimental tests on this topic in collaboration with the group from Politecnico di Milano, guided by Giampiero, and within the DriSMi simulator. So basically, 2 almost professional drivers drive a high-performance car in a simulator environment. We measure lap time and steering effort to understand the trade-off between speed and control. So the main result is simple. Faster trajectories require more steering effort, but robustness changes basically this balance. Okay, so the main takeaways is that nominal trajectory are the fastest, but are the most demanding in terms of effort. The friction robust trajectory achieves almost the same lap time as the nominal, but with much lower steering effort. And driving without reference is both slower and less efficient. So basically, the main takeaway is that disturbance-aware reference trajectories help drivers to drive faster, more smoothly, and more consistently. And we think we have proved that they are available both for performance and for training. So if you are interested in having more details about this topic, so stability and robustness guarantees in motorsport planning and tracking, you can have a look at Matteo Mazzoni presentation on YouTube, basically we have this short curl in order to be easy to remember, or you can take a picture and look at the full presentation on YouTube. And also you have, of course, the reference about the published papers on the left and the one that we have submitted with the colleagues from Politecnico di Milano. Then the second topic that I will leave the stage to Martino is actually the optimization-based methodology to estimate the safe region of attractions of the vehicle with driver system. So if you lose some words in Martino's presentation, you can refer to this link again to this presentation, which is uploaded on YouTube. And this work has been submitted as a paper quite recently. So I leave the stage to Martino, and thank you very much for your attention.
Hello, everybody. I'll try to share my screen. I can share content unless the host or co-host makes you the presenter. So
Ti diamo arriva.
Yeah, grazie.
You could start, I think, Martino. Try to share.
Optimize. Text and images. Okay. Share. Entire screen. Okay, so. Okay, can you confirm that you see my screen?
Yes.
Okay,
Yes.
thank you.
Yes.
So, thank you. I am Martino Gulisano from Università di Pisa, and in this last talk, I'll present our research on sum of square certificates for vehicle global stability assessment. By global stability, we refer to the combined behavior of the vehicle with the driver together, and here we study the simple vehicle with driver model that Professor Della Rossa has already clearly explained to us. So overall, I'll just say that this driver behaves like a delayed feedback controller that corrects the error of a look-ahead point. Okay. And this simple system, as we have already seen, is well suited to simulate lane change maneuvers like this one in this short video. Under certain conditions, this system has an asymptotically stable equilibrium, which corresponds to the vehicle settling on the reference path. And our goal, our aim is to answer this question. So after a very large after sufficiently large disturbances, for example, after a strong wind gust or after a rapid emergent lane change, the driver may not be able to bring the vehicle back to the reference path. And so our goal is to quantify how large a deviation the driver can still handle safely. In other words, we want to estimate the region of attraction, the basin of attraction of this stable equilibrium, which is the set of initial conditions in the state space from which the system evolves to the asymptotically stable equilibrium. In control theory, so this set is defined as the region of attraction. We start from a very simple benchmark system because it allows us to explain more clearly, to visualize the theory because it is two-dimensional. And this system is the time reverse van der Pol oscillator, and it has an asymptotically stable equilibrium at the point, an asymptotically stable equilibrium at the origin, and an unstable limit cycle. So as we can see from the streamlines in this plot, trajectories starting inside the limit cycle converge to the origin, while trajectories starting outside the limit cycle diverge. And so this means that the gray region inside the limit cycle is actually the region of attraction of this benchmark system. We use two key tools to estimate the region of attraction for this benchmark system, and these are Lyapunov functions and the local invariance theorem. So Lyapunov function, I say just quickly, they are energy-like functions whose values decrease along the system trajectories, and they are particularly useful to apply the local invariance theorem. These second key tools add two extra properties to the ones used to define a Lyapunov function, and these two are that are the existence of a Lyapunov level set, shown here as the red region on the right, that is fully contained in the region where the derivative of the Lyapunov function is negative. So this first requirement just says that the red region, this red Lyapunov level set, is included within this purple region. And the second requirement for the local invariant set theorem is that the origin is the only stable equilibrium inside the red level set. So with all these constraints in mind, we can see that the constraint on the uniqueness of the equilibrium is trivial because we have just one equilibrium for the system, and all the other constraints may be recast just as positive definite constraints. So on constraint on the Lyapunov function V and on an auxiliary function L, which depends on the Lyapunov function and also on the system dynamics. For generic function, for generic V and L, these constraints are quite difficult to check. The math behind is really hard. But if V and L are polynomials, then it is sufficient to check or enforce that these polynomials are sum of squares. This means that they can be written as a sum of squared polynomials. Just a quick remark, for L to be polynomial, we also need the system dynamics to be polynomial because this x dot, the system dynamics, is inside the expression of the polynomial L. So how do we check that a polynomial is sum of square? This is very straightforward. We express the polynomial through its gram matrix representation, and this is a quadratic form built on a vector of monomial Z and on a symmetric metric Q. And then we set up and solve a semi-definite program, or STP, where the decision variables are the entries of the symmetric metric Q, and the constraint is just that matrix Q has to be positive definite. There are several software packages to solve this kind of problem, to solve STPs, and we use Python Toolbox Drake from MIT together with the Mosaic solver as backend. Okay, so we need with this tool we can find a invariant set, we can find a level set, we can find a Lyapunov function and a level set which is an inner estimate of the ROA, because all trajectories starting inside this red region will converge to the origin. But the larger the invariant set, the better the ROA estimate, because we know that the gray region, all the region inside this black limit cycle is the actual region of attraction. And so we set up an optimization problem. In this optimization problem, we introduce this auxiliary shape, this blue ellipse, because this blue ellipse allows us to have an objective to maximize, because we know a simple formula for the ellipse area. And so we introduce an ellipse which is constrained to be included within the red Lyapunov level set. And by maximizing the area of the ellipse, because we know its formula, we can inflate from inside our estimate of the region of attraction for this benchmark system. This one is the result. Just a quick remark. We have this set constraint here that just means the blue ellipse is inside the red Lyapunov level set, and also this kind of constraint can be reformulated as some auxiliary polynomial is sum of square. So we want to recast every constraint as there is a polynomial that is sum of square, and this is sufficient to prove the original condition. So we have just one last step to do, because since convex optimization problems are easier to solve, we split this previous optimization problem into an iterative three-step procedure, into an iterative three-step algorithm. So where each step is a convex problem, and indeed easier to solve. In step one, we fix a Lyapunov function, find its largest invariant level set, which is included in the purple region, which is included in the region where the derivative of Lyapunov is negative. Then in step two, with also a fixed Lyapunov function, we find the largest blue ellipse inside this red region. And then finally, in step 3, we update the Lyapunov function, preserving the chain of set inclusion of the ellipse inside the Lyapunov set inside the region where foo dot is negative. And this is on the right the result of the first iteration. And with with next iterations, we have more accurate results. By the 8th iteration, this algorithm has converged, and you can see that the red region now quite exactly matches the black limit cycle, the black limit cycle in the figure. So we have discussed the theory behind our procedure, and now we'll go back to the simple vehicle retrieval system. You've already seen this set of the questions before in the presentation of Professor Della Rossa, and we just need a little lifting to this system, because to apply sum of squares, to apply sum of square constraints, this system needs to be polynomial, and this is clearly not, mainly because the trigonometric functions of the steering angle delta and of the yaw angle c, and for them we can safely use Taylor expansions around equilibrium, and this is a very good approximation, while the challenge is to approximate the lateral forces of the city ground lateral forces, the axial characteristics acting on the vehicle. And to do that, here we in this system, the lateral force were originally described by magic formulas, and a peculiar feature of magic formulas is that they saturate. So for larger values of axial slip angle, the value of the lateral forces converges to an asymptotic value. But polynomials cannot describe saturation. And so we cannot seek a global approximation for our system, but we just look for a local approximation for the central part of the magic formulas. Not just a linear approximation, it's still a non-linear, it's a cubic one, but just on a central fitting range on slip angle. The bound of the fitting range corresponds to 95% of the peak lateral force, so 95% of saturation. And from now on, we will just seek a subset of the region of attraction where this polynomial approximation of the magic formula is valid. And we call the subset the safe region of attraction, because this is the region that we can safely certify with our polynomial approximation of the original non-linear full vehicle driver system. So what are the results of this procedure? Here the iterative three-step algorithm returns a 7-dimensional manifold, because we had a 7-state dynamic system. But unfortunately, 7-dimensional are too much for a plot. And so here on the right, we see just an intersection of the 7-dimensional manifold with a plane, with a very popular plane. We've seen this already before, the yaw rate lateral speed plane. But this blue region here, this sum of square safe ROA, is just an intersection of the entire object. And the first question that we can ask is, how accurate is our source procedure? How accurate is this estimate? And to assess its quality, we compare the source safe ROA, this blue region, with a simulation-based safe ROA, which was obtained via exhaustive simulations on sampled initial conditions on the RV plane. So we took initial conditions on this plane and simulated the system, and just checked if these simulated trajectories were stable, and whether they respected the bounds for the polynomial approximation, because we had bounds for the approximation of the magic formula. And so here we see these yellow and green boundaries. The yellow boundaries means that if we start on the yellow boundaries, we will hit the front slip angle bound that we impose for the polynomial approximation, while starting from the green line means that we hit the rear slip angle bounds. So inside these simulation-based safe ROA, inside yellow and green lines, we can say that this region is a target safe ROA for this system, and we have a quite good approximation with our blue sum of square safe ROA. And of course, this simulation-based method is not really an alternative to compute the ROA, because here we are just computing these boundaries on a two-dimensional plane, on a two-dimensional subspace, while it would be really expensive computationally to sample initial conditions all over the seven-dimensional region. On the other hand, the sum of square safe ROA is just an intersection of an object that we have computed all over the safe space. So it's quite more powerful. As for these, as for the degree of the approximation here near these sharp features near the vertex of the ideal target region, we could improve the approximation by using higher degree Lyapunov function. Here this is a fourth degree Lyapunov function, but this would cause the number of decision variables in the algorithm to explode. So it's not quite a good idea with the current formulation. The second question that we may ask is how restrictive was the domain of validity of the polynomial approximation, because we are imposing some kind of restrictive hypothesis by constraining the axial slip angle. And so we compared again the simulation safe ROA, so the target that we were aiming to approximate, with a simulation-based ROA, via a simulation-based estimate of the full region of attraction, which is represented by these dashed red lines. And here we see that the safe ROA is fully contained within the full ROA. And this means that in this case, these numbers, these plots, are relative to an understeering vehicle. The constraints on the slip angle prevent the system from reaching stability. We cannot reach stability if we do not saturate the axle, and we can go beyond the axle saturation because of the polynomial approximation. And so this is the case for an understeering vehicle. On the other hand, if we look at results from an oversteering vehicle here on the right, we see that we have no more the green lines referring to the vehicle hitting the rear slip angle bounds, but now the safe ROA and the full ROA, these dashed lines, share some boundaries here on these solid red lines. And this means that our polynomial system, our polynomial approximated system, can describe instability along these boundaries. And so we have lost something less for the oversteering vehicle, because the polynomial approximation can describe the vehicle going unstable, while the understeering could not. Okay, so here you can see the oversteering and the understeering case side by side, and appreciate the fact that here how the safe ROA is good with respect to the simulation-based boundaries, and what are the constraints of using a safe ROA with polynomial approximation with respect to the full ROA. To give you some computational times, we perform the analysis, we run the analysis on a laptop with 26 gigabytes of RAM, and each source safe ROA computation required more or less 5 minutes. The understeering case was a bit faster, and 6 iterations of the iterative 3-step algorithm. And as a final highlight, I just want to show some trajectories outside the viewer plane and the main, okay. And here, if we focus on these, on the left plot, we have the yaw rate, lateral speed, and steering angle. On the right panel, we have the lateral position with respect to the reference path, and the yaw angle of the vehicle with respect to the reference path. And if we focus on the pink, orange, and red trajectories, we can see that there are a pair of trajectories. The solid line is the full system, the original nonlinear system, the same that we have seen in the previous presentation, while the dashed lines are relative to our polynomial approximation. And so we can see from both panels that if we start inside the safe ROA, inside the bounds that we have imposed for the polynomial approximation to be valid, the both trajectories, the polynomial model trajectories and the nonlinear system trajectory, match quite good. The polynomial trajectory closely tracks the full nonlinear trajectory. And just as an example, if we start outside the ROA, we have got this gray trajectory that simply diverges as expected because it is outside the region of attraction. So to summarize our findings, we developed a 3-step iterative algorithm for ROA estimates, and also explain how to use a polynomial approximation strategy to apply sum of square method on this vehicle retrieval system. We computed the sum of square safe ROA as a 7-dimensional manifold, so we just have to find an optimal Lyapunov function, an optimal Lyapunov polynomial, and an optimal level set, and we can in a very fast way check the stability of a system just by evaluating this function, this Lyapunov function, at correct state. And we evaluate a polynomial, and if the value is below an optimal level value, we are safe. If it's above, we are unsafe, and we are doomed to instability. The overall vehicle retriever system is doomed to instability. Further works in further works, we'd like to extend the polynomial fitting range, so then the safe ROA would match more closely the full region of attraction. And also, we'd like to reformulate the problem to use higher degree Lyapunov function, so the Lyapunov function could be more flexible to approximate the exact region. And a very promising application would be the integration of this tool as a supervisory level in active control system. So, for example, we could have an active control system that could be switched on as long as the polynomial evaluation of the safe ROA would say that the human driver is no more able to bring the vehicle back on track. And when this polynomial check is no more valid, we could use this signal as a switch on for active control system. As Professor Gabbicini already said, you can find more details on our paper, Global Stability of Vehicle Retrieval Dynamics via Sum of Square Programming. It was submitted, but preprint is available on arXiv. And that's all. Thank you for your attention.
Thank you very much. Okay. This concludes our session this morning. We had a couple of presentations for the 2 projects that we had, and we have no more time for answering questions because the time has elapsed. So I thank you all the participants, both here in Milan and the one that are connected via the web. And let's keep in touch on the with our socials and also with our contact to go on with this very, in my opinion, intriguing and step that we have made in these 2 topics referring to the safety and how vehicles are used by humans. Thank you very much to all of them.